Yes. Sunday lectures. Um, let's start with Al-Fatih and join me in reciting Al-Fatih. Bismillah ar-Rahman ar-Rahim. Alhamdulillah Rabbil Alameen, Ar-Rahman ar-Rahim, Maliki Yawmiddin, Iyaka na'budu wa iyaka nasta'in, Ihdina as-sirata al-mustaqim, صراط الذين أنعمت عليهم غير المغضوب عليهم ولا الضالين آمين. Dr. Jabarin told me that the past month the programs were excellent, attendance was excellent, and I think I attributed that to my absence. So I thought he was trying to tell me that when I leave, things get better. Yeah. So today we have an exciting lecture, and our speaker is none other than Dr. Jabarin. We talked a while ago to have a assigned topic, and who else could talk about chemistry, elements of chemistry, than Dr. Jabarin? And the reason we discussed that was that really, ever since the creation of this world, chemistry has played such a pivotal role in shaping things. Man came on the scene much later, but still today, without chemistry, we will come to a screeching halt, uh, and he will go through the list of things that we don't even pay attention today. That chemistry plays a role. Uh, Dr. Jabarin is well known to you as a founding member of this Islamic Center and long-term president of the center. But not many people in the community know the impact this gentleman has had on the field of chemistry in general and in polymer science in particular. He came from Palestine, according to his own saying, that he had marginal uh, knowledge of English. And imagine that somebody is thrown into an American society where you cannot communicate well. Uh, he went to Dartmouth for his college education, and along the way he had some fantastic mentors. He did his PhD in the University of Massachusetts at Amherst. And after that, he joined Owens, Illinois, where he was the senior research scientist, principal research scientist, and worked there for a number of years. And when Owens, Illinois was in the process of reducing their support of the research, University of Toledo offered Dr. Jabarin to come to University of Toledo as the director of Polymer Institute, which he held for many decades. Along the process, he mentored and served as instructor and advisor for a number of people who came through that institute with PhDs. I mean, this is a huge thing, and I haven't talked to him lately about that, but I think he has how many uh, patents you have? 47. So he had he has 40 patents to his name, and you wonder what else did he do in life? So his topic today is chemistry for everyday living. I forgot to mention one thing, and that is that Dr. Jabarin is a distinguished university professor. Those of you who are not in academic world probably don't know how important that is. There are very few people in any field, and that is not on seniority, that is strictly on standing in the field internationally, that the university will grant them the status of the distinguished university professor. Also, you can spend all your lifetime in academic life and you retire, but very few people are given the status of emeritus professor. So we happen to have both a distinguished university professor and an emeritus professor. Please welcome Dr. Saleh Jabarin.
Thank you very much. Let me start by asking a question. And the question is, what do you think was the first chemical plant? Who created the first or established the first chemical plant?
Like in factory?
Well, as a factory, yes. DuPont. Okay. Yes, DuPont had established many, many plants. But I'm talking about the first one ever created. It's you and I. Our bodies are basically chemical plants. Okay? And Dr. Salman Abdul Wahab is a similar field, really. He is a biochemist. And my organic chemistry professor, undergraduate, he used to say, a good biochemist is good organic chemist. So, it's no different in academia than in any other profession. Everybody thinks he is the best and their field are the best. So let's see what is chemistry? We're going to define that. We're going to define what materials are. And then we're going to differentiate between what we call small molecules versus massive molecules. And really, our body contains both. And you wonder when people say, I have invention. Nobody has invention. Okay? Human being cannot invent. They can discover. Because all things are there. It's just for us to discover them and explain their function, how they work. That's the role of a scientist. So, science can be greatly beneficial and at the same time can be hurtful. Okay. But, as Dr. Amjad Hussain said, science has been with us all our lives, and no human being, nothing could function on this earth without the function of chemistry. Okay? So it is an essential science that goes over many, many fields, and we'll explain that. And then my specialty is polymers. We'll explain what those giant molecules are. We typically talk about salt, sodium chloride, low molecular weight. And it's amazing that we can create what the body has. We can create proteins, we can create synthetic polymers, we can do all of those things. Okay? But when God creates a polymer in our body or an animal, it's perfect in terms of certain characteristics. And illnesses occur because there is some disturbance to this order. So when we make in nature, when things are made, they all are exactly the same. However, when we make synthetic material, we cannot control that. So not every chain is the same length. Okay? So we have a distribution of length. Okay? But when you talk about human protein, it's the same molecular weight, whether it's in you, me, or somebody else. However, the stuff we use every day, that is not fixed. And we'll explain that. So we'll differentiate between the word polymers versus the word plastics, because that is really the common word that you use. And we'll talk about the uses of polymers. I really had a video to show how some things are made. Unfortunately, it's been 15 minutes. So I thought maybe another meeting might be okay, but not this one. It will take too much time. So now we will talk about the side effect of science, okay, which is that global warming. This is a result of our own activity and the way we live. And we'll talk about what are the major sources of that and what you and I can and should do. Okay. And then we'll take a couple examples of things which are really would have been extremely detrimental if we did not realize this ozone layer and what has happening to it. Definitely in the 60s and 70s and late 70s, they discovered that the ozone layer is decreasing, and that is extremely dangerous. The ozone layer protects us from UV light, okay? We need some of it, but we don't need a lot of it. And the ozone layer, it has to have certain density to be able to protect us from the UV. And that was in danger in the 70s. And there were two chemists who collaborated and discovered the reason for that decline. And then industry learned to not use those materials, and therefore the ozone layer is back to normal. However, when we create what they call gases that tend to cover the sky, and therefore we we get global warming because the heat from the earth goes up and gets trapped. And those are gases which are known to all of us, primarily carbon containing gases, CO2, methane, ethane. Uh, Agricultural products will create this. All animals will create it, especially cows. So there are some solutions. If we all become vegetarian, I think this will be fantastic to the environment. But human beings are not going to be all vegetarian. So we need to deal with these kind of things, okay? Then if I have time, I would like to talk to you about things that you see almost every day, not necessarily in Toledo, but sometimes we do have clear skies, and we'll talk about why the color of the sky is blue. And then the last thing we'll observe is many of us are extremely fascinated with sunset because when you look at it, everything is beautifully red, right? Why is that? Okay? So these are the kind of things I thought would be of interest to everybody. So let's continue that. So what is chemistry? Well, it is is study, in other words, people who are specialized in chemistry, they do one of those things. They either study the composition, they study the structure, and the property and the change of matter. Now, what is the matter? The matter, anything exists in the environment which has a volume and mass. So you can imagine then that chemistry deals with the smallest part of that, which is really the basic element in nature. The basic unit is the atom and the interaction of atoms with each other. So when we talk about protein, okay, it has carbon, it has nitrogen, it has oxygen, okay. So it is that interaction that chemists are dealing with. I don't want to scare anybody, but you perhaps seen the so-called periodic table. I only put it so can emphasize to you a couple of things. One, hydrogen, one is carbon, and then this lithium, sodium, and we have oxygen, nitrogen, carbon, and these are the most common elements in nature. Now, this lithium, now is going to be the petroleum of the future, okay? And there are shortages in this element. Right now, the major source of lithium is China, okay? There are some in Brazil, some in Latin America. United States is taking the position that they have to play a major role in the production of lithium. And as you know, lithium batteries are the essential batteries for almost everything we do, especially now with the concern about the environment. Electric cars are the future. And the electric car, the battery is lithium based. There are other experiments going on to see if there are alternatives, but we studied and we lived depending on petroleum for almost 100 years now, and lithium will be that source of competition in the future. So that's all I want to say, the periodic table. But if we look at chemistry, chemistry deals with environmental sciences, earth sciences, in medicine to a large extent, to biology, mathematics, and physics. You wonder how is that? Why is the central point is chemistry? Because really that's what everybody deals with. In other words, if you want to talk about the sky, in order for you to see what's going on, there are a reaction taking place while you are looking at the sky. When you are treating an individual for a certain illness, you are dealing with those chemical reaction and the distortion in those chemical reactions. Okay, so uh, really, but if we take chemistry per se, there are people who are called organic chemists. In other words, they are the people who synthesize or make compounds. And many of the medical field is really filled with medication based on the organic chemistry. Okay. Now, there is another one which is called physical chemist. So, physical chemist will deal with the structure, property of those compounds. Then you have analytical chemist. You see, is the person who will be analyzing it with very sophisticated elements, instrument these days, anywhere from MRI to microscopy to analytical. When you take your blood sample, they put it, they discover that it has in it this, this, and this. Okay, so it's all done by analytical chemists, and now it really requires specialization. In other words, I cannot really do analytical chemistry. I say to myself, I'm part of the physical chemist of the world, okay? Because I only deal with structure, properties, and the like. Okay, so if a material behave in this manner, why does it do that? So science always is based on first assumption. You make an assumption, and then you start experiment to see if the result of the experiment coincide with your assumption. And if they do, then you have achieved a positive result. Now, it does not mean if your assumption did not agree with the result that it's a failure. No, it's a drive for you to change your assumption so that they can do the experiment, and therefore you can find exactly what the cause is in the structure as well. Okay? So many of the so-called inventions typically happened, a lot of them by accident. Okay? Now, we say that polymer material, of course, was uh, on Earth way before anybody thought about this word polymer. Okay? Because organic system from the creation of animals and the smallest part of uh, uh, microbes, and they're small, but they are based on organic type material. Okay, so now let me go back a little bit by saying that when we talk about low molecular weight material, what we mean by that is really anything from medicine to household chemicals to cooking to salt and pepper and spices and everybody who makes a meal every night is doing a chemical reaction. Okay, so you take an egg that looks good, soft and everything. It's made out of protein, and then you boil it. Okay? Then you've made a chemical reaction. How is that? Because the egg is made out of protein, and protein is a large molecular weight type material, and they take a certain form. But every chain somehow is attracted by another chain. So it has on it, there are major bonding, which are those, the carbon to the carbon is called covalent bond. Don't worry about it, it's a chemical bond. But then there are indirect interaction, or those are secondary bonds. And that's what they keep the protein as is. Now, when we boil the egg or we fry it, we break up that structure. And that's we call it denatured protein. Okay? So I mean these are the oldest kind of reaction that we deal with every day. Okay? So Now I come to this word polymer. Polymer is two words, polymer. It comes from Latin. Poly means many, mer units. Okay, that's what polymers are. So they are like, for example, if we take ethylene gas, okay, which is very simple molecule, carbon with two hydrogen one side, carbon two hydrogen one side, and there is what they call double bond. So there is some reaction will take place where you break that double bond to form what they call free radical, and the free radical attacks another one to open that bond, and the chain grows. So now there are, excuse me, there are rules that chemist has to follow, and that will be something like pressure, temperature, okay, and those will control how fast and how slow and how large of molecular weight you want to have. So everybody has a constraint, okay, including molecules when they get it attached to one another. So we have then natural polymers, and these are the proteins, polysaccharides, gums. We have synthetic polymers, which is man-made. Some are called thermoplastic and some are called thermoset. Okay, I'll explain those. Elastomers, there are really two kinds. One is man-made and one is natural. So here's what happened. Before the First World War, rubber was discovered in Southeast Asia. There are trees, just like they take the syrup, it's like a syrup, a little bit thicker than that, but people didn't know what to do with it, okay? Because it's so soft, you have to make it to look like a rubber. So what happened in the First World War, German scientists and Germany was prohibited of entering that part of the world. As a result, they were forced to create their own rubber. Okay? And that really changed everything because rubber is essential. Uh, Everybody will have a car, and the car has rubber tire. Okay? So, where are those materials come from? Okay? So if you look at the total US energy consumption, 33% of the available energy is used industrial. Industrial meaning to make cement, to make chemicals, to make food, to make whatever. 28% of it for transportation, which is everybody's car. And 36% are commercial material because, for example, uh, you take atoms and you make a reaction out of it and use that. Okay? So low molecular weight type consumption, cleaning product, painting, stuff like that. Okay, and the plastic only takes only 3%. So when people sometime when the price of oil goes up or something, they say, well, the chemical industry is really consuming of it. It's not really true. Third of it is transportation, and third for industrial product, and third for commercial. We cannot live without those. Just life will not be, and that's the thing. Humanity is progressing, And every time they start depending on some chemical, it's almost impossible to give it up. Okay? So yeah, people say, well, we don't need this, we don't need that, but everybody uses it. Okay? So if we take, for example, natural gas, which now is really in abundance in the United States. So look at this, 90% of it goes for heating, which the gas is methane. Okay? Whether it's heating plant or heating reactors or heating homes, it's used 90%. And the rest are used for those. So from natural gas, we have ethane, then ethylene, fuel also, then polyethylene. Poly, many units of ethylene. So we have also ethane, propane to make polyethylene, butane to make that, and so on. So the sources are dependent on natural products that existed for a long time. Now, some of us may wonder how come countries which made out of sand, desert, have the best sources of energy? Why is under the sea people can discover gas? What this says that before the sand took over, there was something which decayed with time and got buried underground, and that's the source of petroleum. Now, how long that was? Millions. Okay? And the same thing with the natural gas. Okay? So it is abundant under the sea now, and it's really, uh, there are two threats in this world. One, energy sources, and the second, water resources. We are in the Midwest. We hardly worry about water because we are with the Great Lakes. It's a source of that. There is occasional problem with it, of course. Algae is major source of contamination that decays into low molecular weight type material. And as you remember, about 5 years ago, we had this controversy here, and nobody can drink the water, you can brush your teeth, and all of those things. So my recommendation, I believe that every house should have a filtration system which takes off the smallest of those molecules. So uh, it is commercially available. I use it only for drinking or cooking. The rest of the water is okay because the city water will pass a regulation. Okay, there is no question. They are not sending you anything beyond what the FDA and EPA will approve. And typically, those standards, whether they are in terms of food usage or for consumption of other things, there is nothing called zero in science. Okay? What we mean by zero is that we cannot measure it. So what was zero 50 years ago is now a magnitude which can be detected. Okay? So the standard, they say, is that if, let's say, the content of certain amount of water is so much, let's say, contamination of some kind, the FDA then will have made studies, or the localities will have made studies, and they will experiment, unfortunately, either on human or on animals, and then they set the limit, something like in the order of 10 to 100 times lower than that. So everything is safe. But if you are worried about contamination, then I say is filtration system will be the way to go. Okay. Now, as you know, Ohio, the state of Ohio, is a center for industrial polymer production. In 1839, this gentleman, Goodyear, which is now their Goodyear company, but he was a person, and he discovered that rubber we get from Southeast Asia, we can make it really useful by reacting it with sulfur. Okay? What that does then, it will link one chain with another chain. So there is a cross linking between two chains, and that then will give it the rigidity that is required. Now, we have rubber bands, we have all of that, it's the same. Okay? But some of them are very soft, some are harder, depending on what we call viscosity of the system and how much of cross-linking we have. But anyway, so that was really, and it's in Akron, Ohio. But then shortage of material, then it forced the German to invent their own synthetic material. And real progress really did not start till the 1930s. So polymers have been on the scene naturally from day one, from the day of the creation. Okay? But synthetic polymers have not been known till about the 1930s, where people were able to analyze, and there are some key individuals here. You don't need to remember their names, but you can see 53, 53, 32, 34, and those are important. Polyethylene, nylon at DuPont, okay? And then the list goes on. So from 1930s through the 1960s, synthetic, or people synthesized in the laboratory and then build a plant to produce those. Now, where are those materials used? Okay, well, they are used in transportation, especially now, whether it's the electric car or the gasoline car. Most of the material you see on the outside and the inside are called plastic. Okay? And they are. Now, the word plastic as compared to the word polymer. Okay? So we all take aspirin. I will not take that, but some people take aspirin, which is salicylic acid. Okay? We can make it in the lab, very simple. But that's not the way the pill is made on, right? It will have some other component in it to make it more easy on the body and so on. It's really the same thing with polymers. Polymers are the pure material, okay? But in order for you to make it processable, in other words, to be able to melt it, extrude it, do all of those things, there are some additive to it, and that's why it's called plastic. Now, the word plastic, as you, some of us older people here would remember that the Japanese used to have a priority on that. And they sent to the United States games and dolls and this and that, and they were all bad. So after that, things have improved, but once you give some industry a characteristic, it will stick with it. Let me show you this, the difference between rubber and other materials. So I have here a piece of metal, I put some weight on it, and then piece of rubber, I put weight on it, and gas, press it down with some weight, and expose it to heat. This is at room temperature, and now we're heating it. So we know that if you have a wire rod, if you heat it up with the weight on it, it's going to expand. Okay? And the gas with heat on it is going to expand. But rubber shrinks. Okay? Now, back in the 1930s and 40s, when this phenomenon was discovered, it's exception to every other material we have. Right? So what is rubber? As we said, is made out of long chain, okay? Some of it are connected to each other by their flexibility. So when you stretch the rubber, put weight on it, it expands. When it expands, or the rubber, why is it allowing you to expand? Because the polymer chains go from this random arrangement into slightly more stretched-like arrangement. When you stretch something, you are reducing its entropy, its randomness. And nature likes higher entropy. Okay? Now we are sitting in order here. Okay? Once we're done, entropy takes place. Everybody moves out. Okay? And that's really typical of material. So polymers then have that tendency. When you stretch them like that, they form alignment. And the alignment is kind of forcing the chains to be in order. And when you heat them up, that order disappears. And that's why it shrinks. Okay? Try it as warm, I think you will like it. Now, there are many, many types of polymers. We call them, if they are made only from, first of all, they are made of molecules connected with one another covalently or chemically connected. So if we take masbaha and you make one maybe from here to the entrance, only with the thread connecting them, that's not a polymer chain. But if you glue them together, that becomes a polymer. Okay? But it has to have that flexibility. So we can make things only from one material. If we have the monomer styrene, which is similar to benzene, but it has ethyl group on it, when we polymerize it, it becomes polystyrene. Okay, it becomes polystyrene. We can make a chain made out of two materials. That's called copolymer. We can sometimes make them from three. It's called terpene. Okay. Here's this is a random copolymer. You can see A, then B, all of a sudden A, B. The connection is not regular. Alternating. You see, this is very well designed. This is block. You see, we create a block, another block, and so on. And this is graft, where we have a chain, then we graft on it on the side. These are what make polymers useful in industry. Okay? So when you look at your car and you look at a plastic part of it, especially those fenders and the back, those are made out of more than one material. Okay? Because the industry would like two things. One, strength, liability. So when two cars hit each other at low speed, the plastic may bend a little bit, but they bring it back. Okay? So that is the advantage of it. And this is like how polymers are formed. We call this linear because let's say if I were standing here and walk, okay, I don't have to change direction. Okay, I follow that till the end and do this and so on till here. So if you're driving in that road, you just follow the road. So that's linear. And you see they are together. Now, in this case here, let's say I start at this point. You can come here, you come to dividing road. You turn right or left. Okay, that is called branch. This is cross-linked because what happened is that this chain, the dotted one, is chemically attached to this one. So this, and this, we can process. We can repeat the material. In other words, we can make an item out of it. If we don't like it, we can melt it, make it a bucket. But stuff like this, where we have tight network, we cannot. So all of you have heard of uh, bakelite. This is long time ago. They used to put on the frying pan. The handle used to be made out of that material, and you see you cannot do anything with it. Once you are done, you have to throw it away. It's not recyclable. It's not burnable. It just burns. Now, a tire is not that way. It's slightly cross-linked, slightly. Okay? If we increase that cross-linking, it means now there's flexibility among all of us. But let's say we put connection with ropes, then you cannot have movement, right? If you connect it here, here, and back, that's it. You cannot move. All right. So these are schematic to the thing we have. Now I said that when it comes to the size of the polymer, they are not all the same. And I give you example also of you who like football can relate to this. So we have here uh, X number of players, there are six, right? And one weighs 50 kilogram, and two of them, each one weighs 70, two of them were each one 90, one weighs 140. So their average is 85, which is the simplest way to, you take the total, divide by the number, it's called number average. But in playing football, the weight of that individual, his size, matters. So which average is more important if you're playing football? This is more important, which is called the weight average. You see, it's different. This is 85, this is 94. So now, if you have a polymer that you made in the lab, you get a distribution. Some of them are very short, some are in the middle, and some are very light. So we have a distribution of molecules. And that determines what kind of properties we have. Okay? That does not exist in natural polymers. That nature makes, or God makes. Okay? So let's come to this point because that really, uh, when you buy salt, it's crystallized. Okay? But when you buy oil, it's not crystallized. So there are materials that by nature they are liquid, and whatever you do, crystallization will not happen. But if you take honey, for example, and you put it in the fridge, the sugar then will form, which means that the honey crystallized. You can reverse it, you can melt it. The same thing here. There are materials such as polyethylene, polypropylene, you cannot get them without crystalline state because the rate of crystallization, when you cool them from the melt down, they will crystallize right away. Okay? And that's useful because these are the pipes and other things we make from it. Then there are material which is called amorphous, don't have any order to them, that is PVC, polystyrene, polymethyl methacrylate, plexiglass. That's how we know that material as plexiglass. Right? Now, this is where the important polymers, PET and nylon. Those materials, you can make them without any order by cooling them very fast from the melt, or you can crystallize in two ways. Uh, yeah, we can crystallize in two ways. You see, this is now a random distribution. We can heat it up slowly at some temperature, start crystallizing into sphere-like structure, we call them sphere-like, and then they impinge on one another, and these are thermally crystallized material. They are opaque. You cannot see through them. However, what we can do is take this material and stretch it. When we stretch it, we form small crystals, which are those separated by some disordered material. And these are clear. And this is what that bottle is. Okay, that's PET. Usually it's made out of test tube-like stuff. Then we heat it up to about 100 degrees centigrade and blown to make that shape. The speed at which is blowing is putting some stress on the material, and therefore you create this kind of structure. And then if you cool it fast enough, it's clear. And that's really the advantage of this PET. Okay? Otherwise, it will not be good material to put water in it because if it's opaque, nobody will buy it. Okay. And this is beautiful thing you can enjoy to put a crystallized material under polarizing microscope, and that's the image you get. Okay. And that image will tell us, for example, from here to here is the radius of that sphere line. And of course, not all of them are exactly the same size. All right, that's expected. This is PET. Don't worry about it. It's made out of two monomers. One is called terephthalic acid, and one is ethylene glycol. What is ethylene glycol? We all use it as a coolant for the car. Okay? Yes.
We have 5 minutes left, so 5
Sure.
to 6 minutes.
Yeah,
don't know if
I
we're
think
open
would
for
be enough.
Q&A.
So that is a preform. This is polypropylene, and you see the industry is trying to make it clear. Okay, and that's PET. Big difference between them. Okay, again, polypropylene and PET. So these is crystalline because they cannot cool it fast enough, so it has to be that way. And these are again these are blended materials. What I'm trying to show you here is that the temperature at which you will do that blowing will determine that clarity. Okay? And for the engineering plastic, those are called engineering material, primarily used in automotive and other airplanes and so on. Between the 1920s to the year 2000, people emphasized synthesizing the material. After that, you can see everything is blended together, but that's not an easy process. Polymers behave like human beings. Sometimes people don't like each other. So you have to find a way for them to like. We spent some hours yesterday dealing with that issue. Okay? But anyway, this is the ozone. Okay? So here is oxygen, and this is the ozone. Three oxygen atoms. And you see the sunlight then creates some kind of movement for it to go into this and back and forth. So there's an equilibrium status here, but that ozone magnitude is very crucial because, as I said, that's what determines how much UV light we get on Earth. Okay? And any layer of other gases covering that layer is detrimental. Okay? And this is the effect of those gases on the environment. You can see they go back to the 1980s to 2020, and you can see the temperature on the average increased by 1 degree. Now, when it says 1 degree or 1.5 degree, this is really an average over the whole world. So some region of the world will have higher temperature, some lower. On the average is this. And you can see the trend is absolutely moving in the wrong direction. We need to be like steady at some point. So, uh, blue skies. Let's talk about that one. Okay. The skies are blue. Why? Because even though you look at the sky and you see it's really very clear, it has some particles that you and I cannot see, but the light can see. And as you know, white light, which is sunlight, is made out of many colors, right? The blue is the shortest wavelength, and the scattered light from those particles is proportional to 1 over the fourth power of the wavelength. So the shorter the wavelength, the more scattering you get. So in clear sky, the blue color is doing all the scattering, and that's why you see it blue. Now, what is this? This, as you see, it is sunset. Whoever took the picture as if the sun is where the last chair is very horizontal to your eye, right? So then you are not seeing any of the scattered light, okay? You're not seeing that because you are looking, so there is transmitted radiation. So anything 2.5 degrees from where you are looking and up, that's scattering. Below that, it's transmitted. And in the evening, because your face is almost parallel, although it's not in real, but it looks like it is, you see it as red light. So, if you hear it, you forget it. If you hear it and see it, you remember it. If you see it and do it, you learn it. So, good luck.
We can give about 5 minutes for questions. I know all of you are going to go home and set up laboratories in chemistry.
I was going to ask, is there a way to manufacture plastic which is less polluting for the oceans and the earth? Because right now all plastics are just there, like oceans are full of it, landfills are full of it. Is there any way to do that, or it's not possible?
Well, there is a way, but it's a human behavior. That's what really it amounts to. Because where did that plastic come from? It's not coming from the West at all. It's not coming from the United States. It's not coming from Europe. It's primarily coming from China, India, Vietnam, and so on. So what needs to be done is that for people to learn how to take care of the material. In other words, the most of the plastic you see in the ocean is really coming either from sources of the country or the boats, the ships, because everything they use there, most of it is plastic related, and then they throw it in the ocean, and then it travels all the way to California, all the way here. Now, there are some polymers that you can make that are called biodegradable, but they are not, don't have the properties. So you see, to take out the polymers which are polluting, it means you have to go back to the 1920s. And nobody will agree to do that. So, yeah, yes.
If I may ask a three-pronged question, if I may. First, great presentation. I appreciate it. I learned something. So kudos to you. First question, if I may, on the periodic table, all of the elements, is it known, do they all can combine with one another or not? There's some that do not, some of the
Oh, of
chemicals.
course.
They all can combine.
No, not necessarily.
Uh,
Not necessarily, no.
Second, out of all of the chemicals, plastic specifically, around the world, which nation is the most consuming of those plastic? And then the second, where do you see the advancement of chemistry in, let's say, the next 50 years coming from which nation? Thank you.
Yeah, that's a good question, actually. Uh, there are mixed messages as to who is consuming most. I would say 10 years ago it's the United States and Europe. But now with the advances that China is making, and Chinese society is pretty much moving into so-called the middle range of income, and therefore they want the the convenience of the rest of the world, and therefore that is greatly used. I think that what you and I can do, we say three R's: reduce, reuse, recycle. Okay. Now, reduce, all of us can do that. Okay. I mean, don't have to buy bottled water every week. You can put a filtration system. That's one way to reduce. The second one is reuse. How can we reuse it? Yes, we can. It has been used for a long time. You can take the in state like the northeast and the northwest, they have a deposit state they call it. In other words, when you buy a bottle, you put 5 cents deposit. When you return it, that 5 cents goes back to you. And that is the best recycled material you can have. It would be the cleanest. What they would call curbside recycle, it's usually mixed with all kind of things. Okay? So there are solutions, but it's hard to impose them. Okay? So in Ohio, in Illinois, in all of them, they don't have that. And the industry against it, and in Michigan they have deposit, and it works. So these are the kind of things we all can share. Now, what the rest of the world can do is really for them to be educated on the chemistry of those things, and not necessarily the public per se, but at least governments, to understand there is downside to that, and therefore maybe they can institute some kind of recycling. Or, I mean, China is till recently, at the time of pretty much Trump administration, China stopped recycled material from the United States. And that was really a big controversy because we used to ship everything to China, they purify it, and then send it back to us. Yeah. So I think Ahmed has a question, and I'll come to you next.
So, I've heard, I don't know how true it is, they say that plastic gets into water and when we drink it, or is there a danger of small particles of plastic getting into our system, our blood or our system?
It's possible, but again, I think that in the city water where there are regulations, filtration system before they send it to you will take care of that.
When they talk about bottled water also, they say bottled water, the bottle itself, the plastic bottle,
It releases particles?
yeah,
That's not true.
no, okay.
That's not true. Yes.
I read somewhere where there's a bacteria or a microbe that can eat the plastic. How far are they in there? Because
Good.
it's a fascinating concept.
Very good question. Yes. My last trip was in 2000, the year of the COVID. Yes, I went there in January and I came back in February and everything broke down. So I visited a company, which is a French company, that they are using enzyme as a catalyst to break down the polymer back into the monomer unit. Okay? Which is really the best thing human being can do, is take the polymer, have it go through that process. The effective enzyme, they are not really eating it, they are just utilizing as a catalyst for, because there is also acidic environment, there's heat, so it degrades that, but it felt as a catalyst, let's put it that way. And that French company is leading the industry. There are a lot of effort in the United States as well, but thank you very much.
Thank you, Saleh. It was wonderful. It was chemistry 101.